Swayam Prabha. Digital India. Educated India.
And this will not cover experimental methods but mathematical techniques for flow visualizations. So the first and most important is a streamline. What happened? What happened? I am doing the recording on my PC locally. I am not doing it using Teams. And this is what has been going on for all the lectures. So I don't think you have to restart because okay, so first of all these lectures will be going up on television on DTH channel. So I will edit together many of these clips. So I request you not to interrupt right in middle of something. You can, of course, I'll prompt you when you can ask. Okay. So let us proceed to visualize. Rather, let us proceed to look at some mathematical techniques to visualize flows. Or rather, it's how we can describe flows in this particular framework. So in the Eulerian description, we know that given a domain, we have information about the fluid velocity at all different points in the domain. That is, the velocity is actually a field variable. So at all the spatial points in the domain, I know the information about the velocity, all its components, and how they will evolve in time. So at a given snapshot, if I take at a given time, I take a snapshot of the velocity, I will say have something like this. So the streamline is a line which is tangential to all the velocity vectors. And the meaning of something being tangential to all the velocity vectors, let us try to put it in mathematical terms. So suppose I have a velocity vector like this. I can call it v, I can call it u, doesn't matter. So if I want to find the equation of a line, suppose this is that line, okay, I want to find out the equation of this particular line. So at this particular point, I can say that the ds vector at this particular point, that is the increment of the displacement along this particular curve at this particular point, so ds vector should be parallel to the u vector, because streamline is by definition the line which is parallel to the velocity vectors. And so if this is true, I can write u cross ds to be equal to 0 because they are locally parallel. By locally parallel, I mean to say at this point I have drawn the curve like this, but the curve would be like this if velocity at this point would be something like this. If I know that the velocity over here is something like this, the velocity over here is something like this, the velocity over here is something like this, then the curve in question, that is the streamline, would look something like this. Something like this. So that at all points, it is the increment in the displacement vector along the streamline would be parallel to the velocity vector at that point. So this is the mathematical condition. Let us try to write it down for simple Cartesian coordinates using the good old rules of cross products. So ds component, any displacement ds will have components dx, dy and dz. So essentially ds vector is dxi plus dyj plus dzk, and we must understand that dx, dy and dz are not independent, because I cannot vary dx by a certain amount and dy by only this amount. In order for me to lie on this particular curve, dy must necessarily be this quantity. So dx, dy and dz are such that we will always lie on the curve, which satisfies this particular constraint. So let us proceed with the cross product. It will be this. So the I component is v dz minus w dy. The j component is going to be w dx minus u dz, and the k component is going to be u dy minus v dx. And because each of these components has to be 0, because the cross product is a 0 vector, so this implies that v dz minus w dy is equal to 0, w dx minus u dz is equal to 0, and u dy minus v dx is equal to 0. From this we can conclude that u upon dx is equal to v upon dy is equal to w upon dz, and this gives us a parametric representation of what the equation of the streamline at a given time instant is going to be. It is important to note that a streamline is not a time dependent quantity, meaning I will always define a streamline at a given time instant. So in order to specify how a streamline looks, I must also specify at which time instant I want to look at a flow. The other way of visualizing a flow is quite simple. It's called as a path line. In order to find out the path line, if we have a given flow domain, there is some flow domain, suppose it's something like this. We will inject one particle into the domain. It can be a hypothetical particle, or it can be something which is neutrally buoyant. So neutrally buoyant particle means a particle which is not affected by the difference in density between the fluid and the particle, and we will track the motion of the particle as it goes through the flow. So this is a Lagrangian tracking technique. Why does the particle need to be neutrally buoyant? So suppose the flow is happening like this, and this is the z direction and this is the x direction. So gravity acts along negative z direction. So if the particle is not neutrally buoyant, if the particle is lighter than the fluid, then the particle will have a net force acting like this. So during its conveyance in the flow, the particle will not follow exactly the path of the flow, but it will shift across different streamlines. So if you can imagine, at a given time instant, a streamline is like this, like this, like this. So these are the streamlines. Any particle which originates over here will remain confined to a streamline if the flow is steady. So the particle will travel along a streamline. But if the particle has a net buoyancy force, then the particle will go to a different streamline. After a while, the particle will go to a different streamline, and so on. So despite the streamline being something like this, the particle trajectory will be something like this. So the particle trajectory and the actual flow direction will deviate. Hence, we want that the particle not experience any net force in any direction. So the particle has to be both small, because if the particle is not small, the particle will experience a net drag force. So it will not exactly move with the flow, it will move with a retardation with respect to the flow. So particle has to be both small and the particle has to be neutrally buoyant. This example that I said, that the particle will move on a streamline, I said that this is true for a steady flow, but in any unsteady flow it may not be the general case, because the particle, suppose that the flow is unsteady, the particle at t equal to 0 is over here, and let's say at t equal to 0 the snapshot of the velocity fields gives us these streamlines. So at t equal to 0 the particle wants to go in this general direction, so the particle will end up over here after a small time. But say that the unsteady flow changes its direction from this particular streamline to something like this. Let me draw it with a red color. So at the next time instant, the red color shows the streamlines at the times at the snapshot at t equal to t1. So this is the particle at t equal to t1. This is the particle at t equal to t naught. The white is the streamlines at t equal to t naught. So after moving to a point over here at t equal to t1, it will see that the velocity at this point will be something like this. So then the particle will take a trajectory over here. So the trajectory will look something like this. So the path line and the streamline are significantly different when the flow is unsteady. The path line and the streamline are identical when the flow is steady. Now we've said that we put a hypothetical particle in the flow and we evolve the particle in the flow field. Let us put this in mathematical terms. So the velocity of the particle sampled at a given point, so it will sample the velocity of the flow, because we are assuming that it is a neutrally buoyant particle and a small particle, so that the presence of that hypothetical particle or even a real particle does not affect the flow. If we have a large ball in the flow itself will get affected and we will not truly get how the velocity field looks like. So under these assumptions, the velocity that the particle will sample, it will be the u-v-w velocity at the particle location. So at this particle location, u will be dx dt of the particle, so I will call it p. V will be dy dt of the particle, and w will be the dz dt of the particle. So UVW sampled at the particle location. So let me define the particle location as the x vector p. X vector p stands for x particle, y particle, z particle. And of course, these are ordinary differential equations, so I must supplement these equations with appropriate initial conditions. So at t equal to 0, I must say that the location of the particle at t equal to 0 is some xp naught, yp naught and zp naught. So the particle originates somewhere over here. So this is xp naught. It samples the local velocity, then it moves over here. Again it samples the local velocity, let me call it xp1. Then it samples the local velocity at this point. So the local velocity at this point can change over time for an unsteady flow. It may not remain constant. But the fact is, I am sampling the unsteady velocity at the new particle position and not at the old particle position. So I am sort of sampling the velocities prevalent at the point in concern. So suppose the particle is over here, I am sampling the velocity at the particular point in concern at the time it takes for the particle to reach this particular point. Okay, so at this particular point, if the velocity is like this, the particle ends up over here, say. Then if the particle is some velocity sampled is something like this, it goes over here. Then it samples a particle something like a velocity something like this, it goes over here, and so on. So it is simply finding out the trajectory of a particle, which is nothing but tantamount to doing the same thing in classical mechanics as finding out the Lagrangian statistics. So this is a very easy way of finding out velocities, for example in the oceans. So the ocean, I am drawing the top view of an ocean, just a small section of the ocean. So you might have seen that in the ocean they put neutrally buoyant buoys. So these buoys are designed in such a manner that they experience no net force in the vertical or the horizontal direction. That is, the buoys don't drown or something, they always tend to remain at the surface. The buoys are much smaller, the buoys are quite smaller as compared to the length scale of oceanic flows. So when I say that a neutrally buoyant particle has to be small, it has to be small with respect to the flow. So the flow, you know that the ocean velocities, the gradients in the ocean velocities can span over several hundred meters. So the buoys are typically much smaller than the length scale over which the gradient in oceans happen. Okay. So these are the ocean currents at the surface, and because of this, the buoys will be transported along the direction of the flow. Okay. Because of this, the buoys will be transported along the direction of the flow, and that is how we can find out the surface velocity at the ocean. An example of something which is not a neutrally buoyant particle, but it was very important for us to track, was the disappearance of the aircraft MH370. The fragments of the aircraft were eventually found quite far from what was suspected to be the site of the crash. It was expected that it was somewhere near the South Asia Sea. So eventually it was found somewhere near the east coast of Africa. So the fragments, when they fell into the ocean, the fragments then, because they are not neutrally buoyant, they started sinking towards the sea. So if I draw the cross section of the ocean, so the fragment starts to sink towards the sea, and it samples different velocities as it goes towards deeper depth. So it is not neutrally buoyant, it will not be the same velocity as the surface velocity of the ocean, and it will sample different velocities as it is crossing different depths. Moreover, the velocities in the oceans are all time dependent. So at a time instant you may see that the velocity is something like this. So you may think that a debris particle that may fall over here will travel like this, but no, at some other time instant the velocity might change and become something like this. So the debris particle will initially move like this, then it will move something like this, then after another time instant the velocity may become something like this. So the debris particle will move something like this. So it is not entirely easy for us to determine with only a time snapshot what the particle motion will be. We have to look over entire history of how the particle has sampled all the different velocities in order to find the trajectory of a particle. These ideas would be more reinforced with the help of certain examples, but all I want to say is such kinds of particle trackings are quite important for various exploration missions. The last method of visualization is called as a streak line, and a streak line can be assumed to be a natural extension to that of a path line. Let us first imagine that we have a flow in a domain something like this. Okay, there's a flow in the domain. The flow can be unsteady, no problem. How do I typically visualize flows? What do we do is we put a dye inside the flow. So we take a syringe. So if it's water, we take a syringe, and at this point we push a certain colored dye in the flow. So because of the pushing of a colored dye, the colored dye will be sort of taken with the flow. So I will see, if the dye color is yellow, I will see a line in the flow. So this is how we visualize flows in liquids. If it is air, if I want to visualize the flow in air, I will take smoke and I will try to inject smoke at a point. So smoke will come out and it will show us the direction of the flow. If the flow is unsteady, then the smoke will also go to different directions. But now, what is really happening? When I say that I am injecting colored dye and I am observing how the dye looks like in the flow, what am I really looking at? So let us say I inject a dye at this particular point, and at t equal to 0 to t equal to 1 second, the flow is in the x direction. So the dye, all the particles in the dye will be transported in this direction. Suppose I say that the velocity is 1 centimeter per second. So the length of the dye column will become 1 centimeter at the end of 1 second. So this is the point of injection. Let's say that at t equal to 1 to t equal to 3 seconds, there is a velocity which is in the y direction. So in that case, this dye will move upwards. This dye will start moving upwards, but at the same time there is new dye continuously being injected at this point. So there will be a tail like this also. So this is how the dye would look at t equal to 3 seconds. Meaning I am keeping the injection point fixed. Mathematically what is going on is I am keeping the injection point fixed. I am successively injecting dyes at that particular point. And I am sort of looking at the locus of all the dye particles. Let us magnify the drawing and try to arrive at a much easier viewpoint. So suppose this is the domain and this is the needle of the injection. So at t equal to 0 seconds, suppose a dye particle comes out like this and the flow is in this direction. Now at t equal to 1 second, the dye particle, the red dye particle will arrive at this particular point, but another dye particle will be injected into the domain. So this is at t equal to 1. At t equal to 2, suppose the velocity is unsteady and the velocity direction is something like this, then this red particle would move over here, this orange particle will also move over here, and there would be a new particle which would be coming out at this. So at t equal to 2 seconds, what is the locus of the dye particles that I see? That locus will be this particular line. So this is how I would visualize the flow to be. Now suppose the flow changes velocity and it is something like this. Then this particular red particle will end up over here. This particular red particle would end up over here. Let me erase this particular red particle. This particular particle would end up over here and there would be a new particle coming in over here. So at t equal to 3, the trajectory, the locus of all the points that I will see would be this. So it would seem as if the die has taken this shape. Now suppose at the next time instant the velocity is something like this. The velocity is again something like this. Then this particle would end up over here. This particle would end up over here. Let me rub the t equal to 2 lines. This particle would end up over here. This particle would end up over here. This particle would say end up over here, and there would be a new particle coming in. So this is at t equal to 5. So the locus of all the particles at t equal to 5 would be something like this. So this is the die that you would see. So streak line is the locus of all particles injected at a given point, at a fixed point, at all successive times So this is basically what a streak line is. Now let us see whether a streak line and path line can coincide. Whether a streak line and path line can coincide. Basically what is going on is, if I want to visualize the streak line at t equal to 5, I must inject various particles into the flow domain from t equal to 0 to t equal to 5 at a fixed point. So in order to find the position of this particle, I must sort of obtain the path line for this location. So for this particular point, the path line can be significantly different from the streak line. So the path taken by the first particle could be something like this. But at t equal to 5 seconds, this particle has arrived at this point. For this point, the path line for this particle could be something like this. Meaning, this particle was injected 4 seconds prior to the arrival at this point, at this particular point. So if I inject a particle over here at t equal to 1, at t equal to 5 seconds, it would arrive over here. That is, for this particle to arrive from this, it has taken a time of 4 seconds. For this particle to arrive from here to here, it has taken 3 seconds. And suppose this is the path taken by this particle. For this particle, it has taken 2 seconds, and this is the path taken by this particle. And for this particle to arrive, it has taken 1 second, and this could be the path taken by this particle. And this particle is already at the origin. So the path line for each particle is different because the flow is unsteady. But I cannot really visualize a path line. I can only hypothetically visualize a path line. But I can surely visualize the locus of all the particles, because all the particles will have certain color. So if there is a series of particles I have drawn particles quite separated, but in general the injection will be almost continuous, and so I will see a series of colored particles, and that is the locus that I will see. So I will see a color, a streak of color. Okay, so I must find out the path line for each particle, let it all converge to a certain time at which I want the streak line. The important thing is, for all the different particles, the location of injection is the same, but the initial times are different. Meaning the initial condition for this was 5 seconds earlier to this snapshot. The initial condition for this was 4 seconds earlier to the snapshot. The initial condition for this was 3 seconds prior to the snapshot for this, 2 seconds prior to the snapshot, for this 1 seconds prior to the snapshot, and for this it is at the instant of the snapshot, that is 0 second at the snapshot. So times are all successive. This is what we mean by successive times. So when can a streak line and path line be same? If I have a uniform flow, then I know that a particle injected in the domain, so suppose this is the point of injection, the particle will always keep moving along this line. In fact, if the velocity is steady, this line itself is also the streamline. So particle 1 will move on this line. So suppose at the end of 5 seconds, particle 1 has reached over here. So this is the first particle that was injected in the domain. This is at t equal to 5 seconds. The second particle, which would have been injected 1 second after the injection of particle 1, would reach some distance over here. So this is second particle at t equal to 5, but it was injected at 1 second. This was injected at 0 seconds. Then the third particle at t equal to 5 would be over here, but it was injected at t equal to 2 seconds, and so on. So all the particles which are injected at this particular point would necessarily lie on this particular streamline, because the flow is assumed to be steady. And if they are lying on the same streamline, the locus of all the points injected from this particular point at all successive times prior to the snapshot will also lie on this particular line, and hence this is going to be the streak line. The red colored line is going to be the streak line. As time advances, the streak line will become larger, but it will still coincide with the streamline and all the path lines. So for a steady flow, the streak line lies on the streamline and the path lines also lie on the streamline. So for a steady flow only, streamline, streak line and path line are all identical. For any unsteadiness in the flow, everything will change. The particle trajectory would be different from the streamline, because the streamline would be at different time snaps. The particle trajectory would be different because you are sort of sampling the particle trajectory at a given location of the particle at the prevalent velocity fields. The streak line would successively be the locus of all such path lines, of all such particles that we have in the flow domain. Okay, so any questions so far? Conceptually, do you have any question? What is going on?
So how can streak line and path line be different?
So let us see how. So let us see just a path line. So suppose you have a flow in this direction at 1 meter per second for time period of 2 seconds. So let us draw, and then at the end of 2 seconds, for 3 seconds we will have a flow which will be 1.5 meter per second in this direction. So let us see how the path line for a particle originating at t equal to 0 would be. So 1 meter per second for 2 seconds. So the particle will travel 2 meters, and then for the next time instant it will travel 4.5 meters. So this is the path line of the particle injected into the domain at t equal to 0 given this flow profile. But see, now let us inject a bunch of particles successively at this particular point. All the particles are now, so let us see, for 2 seconds all the particles are injected at this particular point for 2 seconds. So all the particles will move along this line. So the last particle, so at t equal to 2 seconds, this particle just coming out from this injection point would be the particle. This particle would be, so this particle would be the oldest particle in the domain. This particle would have been injected at a 2 second interval. So at all previous times the particles would lie over here. Do you agree with this?
Yes, sir.
Now the velocity would become 1 and 1.5 meter per second for the next 3 seconds. Now the moment I have a 1.5 meter per second velocity, all the particles will start to move in this direction. So all the particles would move 1.5 meters over here. Not only that, but the last particle that was coming out, that particle will move at the same y location of the injection point to over here. But even after 2 seconds there is an injection going on, so all the new particles which are injected after 2 seconds will also lie on this line. So the locus of all the points that I will see is this. So the path line for the first particle is this, but the streak line would be this. Is it clear?
Okay, sir.
Just to put into perspective, the first particle was injected, this particle, the very oldest particle, has now entered into the flow domain for a total time of 5 seconds. All these particular points were successively injected at this point. So the residence time of this particle inside the domain would be less than 5. The residence time of this particle would be less than whatever the residence time of this is. And this particle is just introduced into the domain, just. So what would be the residence time for this particular particle? That particular particle had entered into the domain at t equal to 2 seconds. So this particular particle, which is at the same level at the point of injection, after which all the particles are at a different y location. So this particle would have been injected into the domain at 2 seconds after the first injection, that is 3 seconds before this particle was injected. So 3 seconds before this, so 3 seconds before this, it would have been at this point. This particular point would have been at this point 3 seconds. After 3 seconds, this whatever this point is has traveled from this point to this point, and there is a new particle which originates over here. So all these particles have a residence time of larger than 2 seconds but less than 5 seconds, and this particular point has a residence time of 0 seconds, that is, it has just entered into the domain. So the streak line is this. While each particle has a different path line, the path line for, suppose I want to know the path line for this particle, the path line for this particle would be this particular curve, because this is how the trajectory of this particle would have looked. Okay, this particle would move up, but because it was injected after a certain time before 2 seconds, so it moved slightly up. Then it sees that this flow has changed from 1 meter per second up to 1.5 meter second towards the right, and thus it has traveled like this. So it has not seen the entirety of the 2 seconds of the 1 meter per second flow. It has seen only a part of it. Suppose it has seen only 0.5 second of it. Is it clear by this?
Yes, sir. Clear.
So we cannot visualize path lines directly, we can only visualize the locus of all the points, and so we must know the path lines to understand where at a given time instant all the particles lie in the domain, and then the locus of all these endpoints of the particles is what the locus is, and that is what we will visualize as a color, as a fluorescent dye, or whatever. Okay, so any doubts in whatever we have discussed so far? William, is it clear? Let us consider a velocity field, an Eulerian velocity field given by x. The x velocity is u equal to x upon t plus t naught. The v velocity is v naught, and the z velocity is 0. That is, it's a two-dimensional flow where t naught and v naught are constants. A colored dye is injected. So let me just draw a schematic. So it's a two-dimensional flow, and it is said that a colored dye is injected at a point A which has a coordinate given by x naught and y naught. So the question is, find the equation of the colored line visible in the flow. At t equal to 2 t naught, given that the dye is injected, the dye injection starts at t equal to t naught. The dye injection starts at t equal to t naught and the dye injection goes all the way to t equal to t naught. So we must find out the equation of the colored line visible. So essentially question 1 is asking what is the equation of the streak line, and the second question is what is the locus of a single fluid particle that passes through point A at t equal to t naught. So at t equal to t naught, whatever particle is pushed at point A, we want to know what is the locus of that single point, meaning we have to find the trajectory of a single point, that is the path line for a particle injected at point A at t equal to t naught. So essentially this is to find out streak line and this is to find out path line. Okay, so let's do it. Let us write down first the trajectory equation, that is dx dt is going to be equal to u and dy dt is going to be equal to v. So now if this is true, if a particle is at a certain point, it will sample this particular velocity. So dx dt will be equal to x upon t plus t naught. But now instead of choosing t naught to be fixed, or rather let us not worry about t naught because t naught is a constant. Now when we integrate this, when we integrate all of this, so before integrating let me rearrange. So this gives dx upon x equal to dt upon t plus t naught. When we integrate this, we must integrate it from some variable time ti to a final time 2 t naught, but the particle will always go from x naught to a certain x. What this statement means is that the time of injection is ti. I do not know what ti is. Ti can vary smoothly from t equal to t naught to t equal to 2 t naught. So I will keep it as a parameter. But what this means is the location of injection is x naught comma y naught, and this particular final location x will depend on what ti is. If I choose ti to be equal to t naught, then it is the first particle injected into the domain. So if ti is equal to t naught, then it would mean it is the first particle injected into the domain and it would travel the farthest, or it would be residing in the domain the largest. If ti is equal to 2 t naught, it is the last particle coming into the domain and it would be just at the point of injection. So with this understanding, we must now integrate this particular equation. We can integrate it, so it gives ln x upon xi is equal to ln 3 t naught divided by ti plus t naught. Similarly, we can integrate this particular equation, because this is equal to dy dt is equal to the y component, which is a constant. So if it is a constant, integral dy is equal to integral v naught dt, where y varies from y0 to y. Again, t will vary from some intermediate time, so ti will, so this injection time is bounded between 2 t naught and t naught, and so the integration limits will be from ti going all the way to t, and all these statements that we have discussed will remain valid. So we can integrate the y equation quite easily, and it will give us y minus y naught is equal to v naught t. So this integration should be to the final time, that is 2 t naught, because it has to go from that variable time to the final time 2 t naught. So it will be 2 t naught minus of ti. So now we have the x location and y location of the particle at a final time. So we have x and y location of the particle at t equal to 2 t naught when they were injected at x naught y naught at some variable time ti. So now if I am able to eliminate this parameter ti, I will end up with a locus of all x and y's which have been injected at this particular time at any previous time ti. So we must eliminate ti to find the locus, because ti is the parameter which decides where x and y should be, and this parameterization is very much similar to the parameterization that you have done in mathematics in class 11 and 12 to describe the equation of a circle, that is x equal to r cos theta, where theta is now the parameter, y equal to r sin theta. You can eliminate theta from the equation by squaring and adding. Similarly, we must now eliminate ti to find out the trajectories of all x and y which pass through a point x naught y naught and end up finally at a time t equal to 2 t naught in the domain. How do we do the elimination? It's simple. Y minus y naught upon v is equal to 2 t naught minus ti. This implies ti is equal to 2 t naught minus of y minus y naught upon v naught. Now we can substitute this value of ti into this equation. This means x upon xi. So if I can take an exponential of both the sides, the ln vanishes, natural log vanishes. So we have 3 t naught upon ti plus t naught. So ti is this. So if we add t naught to this, we obtain 3 t naught minus y minus y naught upon v naught, and this becomes 1 upon 1 minus y minus y naught upon 3 v naught t naught. So the equation, also this should be x naught, it should not be xi. Xi I have written it as x initial, but it is actually x naught. So x upon x naught is equal to, or rather x upon x naught multiplied by 1 minus y minus y naught upon 3 v naught t naught is equal to 1 is the equation of this streak line. And the physical meaning is clear. It means that for all injection times Ti. So if this is the point of injection x0 y0, for Ti equal to 2T0, so for Ti equal to T0, the particle at the end of 2T0 will go over here, suppose. So this is the particle which was injected at Ti equal to T0. Say this is some particle which is injected at Ti equal to 1.1 T0. Then this is the particle injected at Ti equal to 1.2 T0. Then so this is Ti equal to 1.4 T0, all the way up to this particular particle which was injected at Ti equal to 2 T0. Then the locus joining these is sort of the curve in which Ti has been removed out of parameterization. The final points x and y are thus related by this particular expression to yield us the streamline. So the green line is the colored dye that we will observe into the domain. Now, how is this different from a path line? Let us find out the equation of the path line, and this is something which you know very well how to do. So we have u equal to x upon t plus t naught and v equal to v naught, and we want to find out the path line for a particle injected at x0 y0, and the path line should be the particle has been injected at time t equal to t0. We want to know the path line of this particle, how the trajectory would look. Now t0 is specified to us. T0 is no longer the parameter of elimination. Let us proceed to see what will be the parameter of elimination. So from this we have dx dt is equal to x upon t plus t0, and dy dt is equal to v naught. So when we integrate the first equation, it is dx upon x is equal to dt upon t plus t naught. We can now integrate it going from x equal to x naught to some value of x, but now the t will go from t naught to some value of t. So let me call it tf to signify the final time. So this integration will give us ln x upon x naught is equal to ln, so let me call this as xf, so it will be xf upon x naught is equal to ln tf plus t naught upon t naught plus t naught. This implies xf upon x naught is equal to tf plus t naught divided by 2 t naught. Similarly, we can integrate this equation and it will be integral dy is equal to integral v naught dt. Y will go from y naught to yf and t will go from t naught to tf, and this will be yf minus y naught is equal to v naught times tf minus t naught. In order to find the trajectory of the particle, I know that the trajectory of the particle is now not parameterized by the initial time, but it is parameterized by the final time. That is, whatever final time I take, I will end up with a different point on the path line. So if I take a final time tf which is quite large, I will end up with a trajectory which is quite long. If I take a tf which is not that large, I will end up on the trajectory which is somewhere over here. So suppose I take tf is equal to 2 t naught, maybe it is over here. Say I take tf equal to 1.8 t naught, it is over here. Tf equal to 1.7 t naught, it is over here. Tf equal to 1.5 t naught, it is over here, and so on. So depending on the choice of tf, I will end up with a solution for x and y which will necessarily lie on the same path line. It's all a matter of now eliminating the final time to find out the trajectory. So let us write down Tf in terms of the other parameters. So Tf will be equal to Yf minus Y0 divided by V0 plus T0, and this particular value of Tf we can substitute in this particular expression. So we have xf upon x0. So Tf plus T0 will give us Yf minus Y0 upon V0 plus 2T0 upon 2T0, and this gets simplified to 1 plus Yf minus Y0 upon 2V0 T0 divided by 1, or this divided by 1 you can simply get away with. So all the x and y, so let me write down the final solution. Xf upon x0 is equal to 1 plus Yf minus Y0 upon 2V0 T0. So all the pairs of x and y will lie on the entire curve that we have shown. If you do not want to draw the entire curve for all particular times, so when you have removed the parameter Tf, you are essentially obtaining the entire curve for all possible times. To know where exactly the particle lies, you tell that okay, I want to know where the particle lies at a time equal to say 3T0. Then you have to revert back to the original equations which were in terms of the time. We cannot make use of this equation to pinpoint where the particle is at a given time, but rest assured, the particle will lie on that same curve, and that curve is the equation of the path line. This was the equation of the streak line. All the different initial points will lie at t equal to 2t0 on this particular green curve, because these are parameterized as per the initial time, while the path line is parameterized as per the final time.
Let us consider a velocity field with u equal to x times t and v equal to y. The meaning of this velocity field is that the x velocity starts off with 0 at t equal to 0, and it increases as time increases, while the y velocity is constant at a certain y. It increases as y increases, but the x velocity increases with an increase in x, and it increases over time as well. Have a look. A particle in this kind of velocity field, initially the particle has a tendency to move towards the y direction, and it accelerates in the y direction because the x velocity is small due to t being 0. Now as time increases, the x velocity starts to dominate over the y velocity, and hence you see that initially the trajectory is more towards y, the slope then starts to smoothen out and it's towards x. So the particle trajectory looks like a parabola. Consider another particle which is injected at some other time, we see that it immediately starts to move towards the x direction because at a later time the x velocity dominates over the y velocity. It shows a bunch of particles injected at the same point at successive times. The line joining 1, 2, 3, 4, 5, 6, 7, 8 till 15 is the streak line. It is seen that the first particle moves more towards the y direction, while the later particles move less and less because they are influenced more by the x velocity. It is unsteady, and hence the streak line and path line will be different. Let's see. Each of the particle comprising the streak line has a different path line. The path line for 1 is shown, the path line for 2 is as follows, and similarly 3, similarly 4 and 5. Each of them has a different trajectory, but at a given time snap, the end point forms the locus, which is the streak line. Clearly see that if the flow was steady, the path line and the streak line would have coincided.